Good afternoon. In my case, it's afternoon. I will describe a little bit about innovations in concrete support structures for offshore wind turbines. And I promised in the abstract also to say a few words about marine concrete structures in general. I think that is important because that improves the possibility to design exactly for the purpose. Ton and I, we work with Dr.techn.Olav Olsen. It's a Norwegian structural consulting company. We have been working with all sorts of structures, also marine structures. And in our mind, offshore wind energy is important. Offshore wind energy structures require marine structures, and concrete has proven well suited for marine structures. And marine concrete structures have some peculiarities that need to be addressed, and some of those are loading, design, and construction. And fortunately, we know how to deal with these peculiarities. Dan and I know each other from many years back through academic work, I would say, and some practical work also. A couple of years back, FIB produced a Bulletin 91, Floating Concrete Structures. It is a very general bulletin. It is helpful, I would say, if you are working with floating concrete structures. There is also a major chapter there on floating wind mills. People have used the sea for thousands of years. The ship to the left crossed the Atlantic some 500 years before Columbus. The little boat on top is Lambot's concrete boat from 1846. And you see up to the right is the Mulberry Harbor that the British built and sailed and to aid invasion of Normandy during the Second World War. And the highway you see is a floating bridge in the state of Washington. And to the right, you see a harbor extension of Monaco. And as you know, Monaco needs space. And all of these usages are defined. They are different, but they are defined. The Bulletin 91, FIB Bulletin, identified 12 areas of potential usable application of marine structures, and they are listed here, and many of them are related to the environment. Now, for marine structures, these are some examples of those structures that we have designed. Most of them are for the oil and gas industry. At the bottom there, you see somewhere between 3 and 4 million cubic meters of concrete marine structures. And many of this is based on, I would say, good structural knowledge and also good knowledge of shell structures that are very efficient at carrying distributed loads, as is hydrostatic pressure, self-weight, wind, snow load, and what have you. And not surprisingly, weight is extremely important in offshore concrete structures. The structure to the left weighed 1.5 million tons when it was transported several hundred kilometers. The one to the right lifts 22,000 tons, 150 meters above sea level. So we utilize, for all it's worth, the effectiveness of shell structures. Construction is very important. We can very rarely build the structure on the site where it shall be functioning. So we need a dock of some sort, maybe a graving dock. And there are several options, and we have listed some of them here. Small structures can be built on a dock and lifted. Larger dock structures that are long but not wide can be built in ship dry docks. The real problem is the very wide structures. You see some examples here. The upper left is a small fish farming bucket weighing 250 tons, lifted by a sea crane. And then you have a couple of pictures of ship dry docks and a couple of pictures of larger dry docks. The dry docks represents a major cost element and also a major risk element, because the cost is fluctuating as a result of the market situation. Our first meeting with the offshore wind turbines was not for a turbine park, but for the electrification of offshore oil and gas installations. Offshore oil and gas installations, they use gas, their own gas, to put it that way, for energy production of the factory on top. And that takes a lot of gas, and the gas emits, obviously, CO2. And some of the operators are looking for electrification of that factory. So one or two, maybe, wind turbines for each location, for example, like this. The sea bottom ones, they are very similar to the platforms that we've been designed for 50 years. It's not a big deal. You need to account for construction, installation, towing, and all the other things. Recently, we've been working a lot with the floating wind turbine, and it is floating in a way that you provide buoyancy and stability by swimming areas, as opposed to a spar platform, a deep pencil-looking platform. And the benefit of that is that you can equip the installation while laying alongside a dock. You can even sink it partially and avoid very high cranes. And you can easily adjust the concept by placing the swim areas different distances from the center. And it is actually quite flexible. To the right here, you see some model tests in wave laboratories, and that is also a favorable issue. It moves comfortably less than a pencil-looking generator. When we're doing design, we obviously start with conceptual design, and you will need to be brave. Conceptual design using very conservative methods are rarely successful. You need to recheck, of course, that you've been not too brave. Design of marine structures is, as I mentioned, a little bit different compared to land-based structures. One of them, of course, is all the hydrostatic loading, and it's a lot of them. You need to balance the structure, and some of you have been in small boats being filled with water, and it may not be very comfortable. And you have, of course, post-net tensioning and accelerations and all the rest of it. The picture to the right may look like an accident. It is not. It is a trick to avoid the very large gap in hydrostatic stability when you submerge the caisson. The large drop in stiffness would have tilted the platform anyhow. So you need to balance. Buoyancy is a beautiful thing, but you need to balance. You obviously need to have weight equal to buoyancy, and you need to relate to where weight and buoyancy is located. And from a design point of view, when you have a structure where the result of your conceptual design also represents the load on the structure, you may be sort of a double winner if you go the right way, or a double loser if you go the wrong way. The figure to the left was made in the late 1980s. The Norwegians were approaching the deep trench for their old platforms, and we needed high-strength concrete and lightweight concrete. And the two circles in the middle represents the effect of increasing strength and reducing weight. And it is looking dramatic. It is actually even more dramatic because the wave loads and some of the other loads are also reduced drastically with a reduced cross-section. Another example on the right, a square floating box. It may be tempting to increase the thickness of the wall to decrease the amount of reinforcement. And because of the weight of the box, the slender box is actually cheaper than the robust block. You can use styrofoam. You use advanced design tools to maybe manage with just one layer of reinforcement. And then we have, of course, some DNB. Then you refer to DNAGL. DNB is Norwegian, actually. I think you said it was Danish. It's not very important. Other type of marine structures, I'll hurry up a little bit. We are doing quite a bit of work on this one now. We have succeeded receiving a large sum of money from EU research and development, 25 million euros. Not Olav Olsen alone, but a large consortium, and we shall build a full-scale demonstration. Here are the companies in the group. Flagship is the name of the project, and we shall build an 11 megawatt turbine, floating demo, and we are really looking forward to results of this work. Quite substantial power in the companies in the group, and we are considering a future with quite a bit of activities. And with that, I thank you for your listening. Thank you.